Hello and welcome back to Quay Does Leetcode. Today I'm doing problem number 295, find median from data stream. So the median is the middle valued in an ordered integer list. So if you're given an array 2, 3, 4, the median is 3, and if there's an even number of elements, then you take the two middle and you add them together and you get that, and then divide by 2. So you take the mean of the two median elements, and the median is the average of those. So between 2 and 3, the median is 2.5. So in this problem, you need to make a data structure that finds a median. So it supports three functions. First, you initialize the median finder object. Then you can add a number. So this number takes the integer num and takes it from the stream and puts it into the data structure. And then this last function, find median, returns the median of all elements so far. So, for example, say you have a median finder object and you add 1 to it. So you add 1 and then you add 2. If you find the median at this point, the median is 1 plus 2 divided by 2, which is 1.5. And then if you add 3, now you return the median, and the median is 2. It's the middle value. So how can we solve this problem? Well, the brute force way to do this would be to have a ordered list, a sorted list. A sorted list. And you always are keeping your list sorted, and you know what the median is because the median is the middle value, or it's the two middle. If it's an even number, it's the two middle ones, the average of those. So what you can do is have an ordered list, and you can do just like we were showing. So you have an empty list at first, then you add 1 to it, and then you add a 2, and you're like, well, where should I put that 2? Well, you look at 1, and 1 is less than 2, and then so you put the 2 after the 1. So then you put a 2 here, then you get the median, which is, since it's even, you take the two middle ones, which are the only ones in the list, and divide by 2, and that's 1.5. And then you add a 3. So you check 1. Is 1 less than 3? Yes. Is 2 less than 3? Yes. You're at the end of the list, so you add 3 to the end of the list. So you add 1, 2, 3. Now, how efficient is this? Well, your add number actually takes O of n time, because you have to be checking, you have to look at each number in the list potentially to see if it's less than the number that you're adding. So you can put the number in the right spot. So that potentially takes O of n time. So the question is, can you do better than this? So, in fact, you can do better than this, better than O of n. So how can we do better than O of n? Well, what are some other ways to keep track of uh, a median? Well, we could have two heaps. Two heaps. So we could have, instead of one list, we could have two heaps. And heaps give us either the min or the max in O of 1 time. And if you have two heaps and you have one heap that is a min heap, and you keep track of, if you have two heaps and you divide the list, you divide the numbers into two heaps. One heap is the small heap, and all the numbers in the small heap are numbers that are less than all the numbers in the large heap. So every number in the small heap is less than the numbers in the large heap. And you should divide these heaps about equal. So you should make them about the same size. So you're dividing it about equal, where only one element, they can only differ by one element. So what if you had a list 1, 2, 3, and you wanted to divide this into a small heap and a large heap? Well, you could have in the small heap, you could have 1 and 2, and in the large heap, you could have 3. And so, how can you get the median of a number of the list, of the entire list, using a small heap and a large heap? Well, if your small heap is a max heap, then it can give you the max in this list at O of 1 time. So, and if your large heap is a min heap, it can give you the minimum in O of 1 time. So what is the median? Well, if your list has an odd number of elements and it's only differing by 1, that means one of the heaps is larger than the other. Whichever heap is larger than the other actually has the median element in it as its max or min. So in this case, the small heap has the median element. The median element is 2 because its max element is 2. What if it was only, there was 1 in the small heap and there was 2 in the large heap? Well, then you take the max, which is 1, plus the min, which is 2, and divide by 2, and that gives you 1.5, the median. So what you need to do is you have some rules. So rule 1 is the size can only differ by 1. And number 2 is every element in small must be less than large. And if you follow these 2 rules, then you can always find the median in O of 1 time using the properties of the small heap and the large heap. So what if your, so what you can do is by default, so how do you make sure your heaps are always adhering to these properties? Well, what you can do is you can by default put an element into the small heap. So let's try this example 2, 3, 4. So I'm adding 2 and I put it in the small heap. Now let's see. The size of the small heap is 1. The size of the large heap is 0. So they are differing by 1. So it's doing that property. And every element in the small heap, there's no elements in the large heap, so you don't have to worry about that. So now let's add a 2. So now we're adding 2 to the the 3 to the small heap. Now the size can only differ by 1. So now there's 2 elements in the small heap and there's 1 element in the large heap. So what you need to do is you need to pop the max element off of the small heap and put it in the large heap, because there's too many elements in the small heap, and the small heap is a max heap. So you can get the max element in O of 1 time. Well, you can pop it in O of log n time, but you can know what it is in O of 1 time. So you pop it, and you pop it from the small heap, and you put it into the large heap. Now, the size they're equal, and every element in the small heap is smaller than the large heap, because 2 is less than 3. So now let's add 4. So we're going to add it by default to the small heap. Now, you look in the max element in the small heap and the min element in the large heap. Is the max element in the small heap greater than the min element in the large heap? Yes, it is. So that means that it's not adhering to the second property. So what you need to do is you need to pop this off of the small heap and you push it onto the large heap. Now, the min element, so now it's adhering to the property because 2 is less than 3. So the max element in the small heap is less than the min element in the large heap. So that's how you do that. So now it's adhering to the property, and so now we're going to get the median. So the min heap has more elements, so that means the median is located in the min heap. And if we take the min element of the min heap, that will give us the median. So the median is actually 3, and that's the correct answer. So that is the algorithm. And so now I will show you how to code it up. So the first thing that we need is we actually need a max heap for the small heap. And Python does not come with a max heap data structure. So we're going to have to implement that ourselves. So we're going to make a max heap data structure, and we're going to do an init function for it. and we're going to be using, whoops, we're going to be using a the min heap. So Python does come with a min heap. So we're going to be using the min heap, and we're going to be altering it a little bit to make it a max heap. So we're going to need our heap elements, so we can just use a list for that. So self.heap, this is going to be all of our elements in the heap. It's going to be just a list. And that is what we're going to need. So now we're going to define our push function. So we're going to, so when we push onto our heap, we're going to call our heap queue, that's our min heap. So we're going to call our heap queue dot push, and we're going to use our self dot heap as our heap, and then we're going to actually so we're going to push a value on to the heap. So we're actually going to multiply this value by -1. What that's going to do is it's going to it's going to make our min heap act as a max heap. If we multiply our values by -1, then the largest value is going to become the smallest value. So we're going to actually push our value multiplied by -1 onto our self.heap. Then we're going to make our pop function. So for our pop function, we're going to return our heap queue dot, whoops, this should be heap push. So this will be heap pop. So we're going to pop from our self.heap, and once we pop, we're going to also need to multiply it by -1, because we want to get the original value that we added to the heap. So when we pushed it, we multiplied by -1. So when we pop it, we also need to multiply by -1. Now we're going to define our top function. So this will give us the top of the heap. So this will give us the max value in the heap. So we're going to return our self.heap at 0. That will give us our max, and we're going to multiply it by -1, because again, when we put it in, we multiplied it by -1. So we're going to need to multiply by -1 again to get the correct thing. And we're going to find one more function. So this is going to be length, and we're going to return the length of self.heap. So this is all that we need for our max heap. So now we have a max heap. So we're going to, in our median finder class, in our init function, we're going to define our small heap as a max heap. And we're going to define our large heap as a min heap. So we can just define it as a list, because we're going to be using our min heap library functions for this. So now we're going to do our add number function. So for this, like we did in our algorithm, we're going to always add to our small heap by default. So we're going to take our num, and we're going to do self.small. We're going to do dot push So we're going to use our push function and we're going to add our num. So now we've added our num to our small heap. Now we have two conditions that we need to make sure. We need to make sure that all elements in the small are less than large than all in large. So basically our max, so our max element in small needs to be less than min in large. That will ensure that all the elements in small are less than all the elements in large. So we're going to check if self dot small dot length is greater than 0 and self dot large. So if we have both of those, and so if they both exist, and if the self dot small dot top is greater than self dot large at 0, then we know that we need to, we have an element that's too big. So we're going to say our too big element is equal to self dot small dot pop. So we're going to pop the element that's too large, and we're going to push it onto our self dot large. So self dot large dot heap q dot heap push self dot large. We're going to push our too big element onto our large heap. So now it should be, if that element that we pushed onto the small heap was too big, now we're going to put it into the large heap. Now we're going to check the other condition is the lengths of the two heaps must not differ by more than 1. So we're going to check if self dot small dot length, this should be a function length, and we're going to say math dot absolute value if the absolute value of the small length minus the length of self dot large is greater than 1, then we know that one of them is too big. So if that's the case, if the self dot small dot length is the one that's greater than length of self dot large, then we're going to pop. So we can just take this from up here and move it down here. So we're basically going to do the same thing. We're going to pop from the small heap, and we're going to push it onto the large heap. Else we know that if it goes into this if statement, one of them is larger. So if it's not this one that's larger, it's the large heap that's too large. So we're going to do we're going to do heap q dot heap pop self dot large, and we're going to push. So we're going to say self dot small dot push too big. Okay, so now we handled all the cases of every stipulation. The max element in small is now all the elements in small that are less than large, and they're the same length or about the same length, only one differing. Okay, so now we're done our add number function. So now we're going to find our median. So basically, we're going to check if self dot small dot length is greater than the length of self dot large, then we know that the median is the top value of self dot small. So self dot small dot top, return that. Else if, well, we don't need to do else if because we returned, so we can just do if self dot large dot length, or length of self dot large, is greater than self dot small dot length. If the large one is the one that has the extra element, then its top element is the median. So self dot large at 0 is the median. Otherwise, they're the same length. So if they're the same length, then we take self dot small dot top plus self dot large at 0. We add those two together and we divide by 2. And that's how we get our median. So our find median is always going to be an O of 1 operation because we're just getting the max and min of the small and large. And so now we're going to, so this is all the code that we need. So let's run this and see if we have any bugs. So I think you can just do absolute value like this. And and I forgot to put the parentheses after small dot length there. Okay, so this is giving us the correct answer. Now let's submit. And it was accepted. So that is how you solve that problem, using more efficiently using two heaps. And your time complexity for add number goes from O of n to O of log n, because it for pushing and popping off of the heap, it is O of log n. So thanks for watching, and I'll see you in the next video.